So now that we've talked about reactive programming, we talked about reactive streams, the reactive streams API, popular implementations of reactive streams, let's return back to our original coverage of reactive programming principles, and we will show how to map reactive streams programming features onto those reactive programming principles. So hopefully you'll see how it all fits together. And basically, we're going to focus on RxJava and Project Reactor, and we're going to map their feature sets onto the principles. They're very similar, but not identical, which is a bit frustrating, but oh well, that's the way it works. So the first principle you may recall was responsiveness. And responsive or responsiveness basically means not blocking so that you'll end up chewing up threads and making the user have to wait and causing all kinds of perturbations in the system because you're blocking. Blocking has all kinds of potential downsides. In particular, we'd like to try to avoid blocking code, especially the caller, the one making the call, because blocking will underutilize processor cores unless you have virtual threads. Traditional blocking would take a thread and dedicate it to just waiting and doing nothing, which impedes the inherent parallelism in a platform, and depending on various factors, could complicate program structure. There's pros and cons each way here. Blocking appears intuitive because it's very much like normal function call invocations on standalone programs. But when you start doing this in networked programs, you can end up getting yourself in all kinds of trouble because you have to have lots of threads running around. So we don't typically want to block the caller if we can avoid it. So non-blocking, this is the non-blocking logo, we're not blocking. The way you do this in Project Reactor and RxJava is by using various operators. And the operators are things like subscribe on, publish on, and observe on that can be used to tell the reactive stream not to block the caller code, but instead to run things in background threads, which are typically running in a pool of threads where the pool is usually something around the number of processors or number of cores on a processor, give or take. We'll talk more about that later. So that's how you can avoid blocking, by using these operators in a stream pipeline. Something else you might want to do, or not, again, there's trade-offs each way, is avoid changing threads. So often, not always, but often, you want to avoid having a situation where each operator that works on an event runs in a different thread in a pipeline. And the reason why that's problematic is moving events or data between threads can incur lots of extra overhead. So you have overhead like synchronization overhead, which might be used for things like bounded buffers to synchronize them, to make sure that you can't remove something from an empty buffer or put something into a full buffer. There's also the issues of context switching, moving from one thread to the next. That's a non-trivial operation. And memory and cache management also makes it more expensive to move stuff a lot between threads. And the way you can do this is you can get fine-grained control over what threads your events run in, once again by using subscribe on, publish on, and observe on. And there's a whole art to doing this, and we'll talk about that when we get into the details in more glory. So that's basically responsiveness. And the long and the short of it is figuring out how to avoid blocking and making sure that you run in a way that doesn't change thread context too much are the ways to get improvements in responsiveness and honestly in throughput as well. The next topic is resilience. So how do you keep your system from failing as a whole when some piece goes awry? So how do you avoid complete failures from partial failures? If partial failures occur, that's the norm, but you'd like to prevent them from becoming complete failures with the domino effect, where one failure causes everything else to fall down. The way this is done is through exception methods. And these methods are designed to make systems more resilient to failure. You're probably familiar, hopefully you're familiar with traditional exception handling in classic Java or classic C++, where you have some kind of try-catch block, and when some operation begins, if it fails, an exception is thrown, and that exception is caught somewhere up the stack of activation records. That's the traditional way of doing things. The problem, of course, is in an asynchronous environment, you typically don't have any connection between the thread that invoked something and the thread that is going to receive the exception, because they're asynchronous. So we have to have exception handling operators. And there's a whole slew of these operators, which we're going to talk about in great detail. In general, our discussion of reactive streams, at least for the moment, will be localized to a single process, not a cluster. When we start using webflux, of course, then you can expand the scope over which failures propagate. And there's a whole slew of these exception handling operators, which we'll talk about. Of course, they're slightly different between RxJava and Project Reactor, but oh well. Next principle, elasticity, which is really about auto-scaling. You want to be able to allow higher workload to take more processing resources, especially cores, in order to be able to give the users the impression that your system can auto-scale as the load goes up. And the way we do that with both RxJava and Project Reactor is by having a pool of threads that are multiplexed atop a set of processor cores. And the asynchronous computations, these operators that are running, can run in a pool of threads. RxJava has a whole slew of different thread pool types. There's a computation pool for computation or CPU-intensive tasks. There's an I/O pool for I/O-bound tasks, and they have different characteristics in terms of how they grow or not grow, and so on. Project Reactor also supports a whole slew of thread pool schedulers, as they're called. Both of them are called schedulers. Ironically, they're not the same names, but they do more or less the same thing. So with RxJava, you also have ways of being able to have a fixed pool for computation or CPU-intensive tasks or operations. And then there's also one that can be elastically expanded for I/O tasks, and so on and so forth. And there's a whole slew of them. We'll talk about them later. And then the final principle that we're going to map stuff onto is the message-driven dimension. And if you recall what I talked about before, message-driven is a little different from the other three principles because it's not a principle as much as it is an implementation detail. How do you implement things under the hood? Implementations of reactive streams like RxJava and Project Reactor, as well as bits and pieces of Java that can be incorporated by reference into the reactive streams frameworks, like the fork join pool, use message passing internally to provide the capabilities and scalability and location transparency and so on for the abstractions that they are offering to the users. So just as a simple example, not the only example, but one example, Java's fork join pool uses messages internally to take the tasks that are given to it, the fork join tasks, and be able to run them in a pool of worker threads, which are basically platform threads. And these worker threads can steal the messages, the fork join tasks that are in different worker threads double-ended queues. They're work queues. And this gives a lot of flexibility to try to keep the overall system humming along, maximally utilizing the processing resources of the threads. So, and there's similar things that are used with RxJava and Project Reactor in the way that their APIs are implemented. What's interesting about this is that the programming model that you see as a developer using RxJava and Project Reactor is method-oriented. You're making method calls, which are basically these operators. But under the hood, there's all kinds of interesting messaging taking place that you don't really see as a programmer. So the message-driven aspects are really hidden and encapsulated from you largely by a method call API. You don't really work with messages directly, which is fine. But just be aware that there's messaging taking place under the hood for a whole bunch of reasons, not the least of which is queuing things up in case you have temporary bursts of data that need to be smoothed out by queuing. Okay, so that's the overview that maps the reactive streams concepts, the features from RxJava and Project Reactor onto the 4 reactive programming principles.